Hello everyone, I'm Haodi Lu, a PhD student of Huazhong University of Science and Technology. Today, I would like to present my paper, Fast Distributed Transactions for RDMA-based Disaggregated Memory. In monolithic environment, computing resource and memory resource are tightly coupled within a single server. It simplifies programming, but it also limits performance. As shown in the left figure, server 1 has to go through server N CPU to access data 3, introducing additional latency. To address these limitations, resource disaggregation offers a better way. It copes monolithic servers into computing and memory nodes and connects them by high-speed networks. Now, server 1 can directly access any data in the memory node. By pooling different resources, the disaggregation method improves resource utilization and facilitates resource scaling and failure isolation. In DM system, computing node must rely on distributed transactions to access shared data in the memory pool for consistency. However, memory nodes usually have limited computing resource, making them unable to handle costly transaction operations. So, traditional RDMA-based transaction systems are unsuitable for disaggregated memory. Moreover, transaction systems should offer low latency for mission-critical applications. This requirement makes it difficult to deploy transaction system in the DM due to the following challenges. The first challenge is that multi-phase transaction processing can cause multiple network round trips. Transaction systems usually adopt optimistic concurrency control and the primary backup replication to guarantee high availability. They process a single transaction in 5 phases. As shown in the figure above, coordinators execute the transaction in the execution phases, serialize the transaction in the locking and validation phases, and finally commit the transaction in the commit phases. Recently, the state-of-art system Ford is designed particularly for processing transactions in DM systems, but it still requires 3 round trips to process a single transaction. The second challenge is inefficient data centralization in the commit phase. To commit a transaction, previous work relied on memory node CPU to update the new data with redo logs locally. In disaggregated memory system, memory nodes don't have enough CPU resource to perform data copy operation. So, coordinators have to send the log and the new data from computing node to all memory nodes. As shown in the right figure, it takes 2 rounds of data transfers. This can cause heavy load on the RDMA bandwidth when the network traffic is heavy. Number 3, limited computing resource make it difficult to schedule transactions. In disaggregated memory system, computing nodes use RDMA compare and swap to require logs with blind retries instead of the remote process call. This leads to high tail latency and even starvation problems. Especially for mission-critical transactions, their execution priority should be enhanced to guarantee low latency. Since there are not enough CPU resources to schedule different transactions globally, it is difficult to accelerate mission-critical transactions in the DM environment. To address the above challenges, we propose HDTX, a high-performance distributed transaction system for RDMA-based disaggregated memory. The right figure shows its overview. At first, HDTX initialized the data store and the network. Meanwhile, the computing pool caches the metadata of the data store for remote data access. After HDTX is initialized, coordinators are ready to serve client requests. When receiving requests, the coordinators fetch and lock the data from the memory pool with priority-based locking, and then execute the transaction locally. Once the execution is completed, the coordinator uses our fast commit protocol to commit the transaction, and then returns the output to the client. Finally, the RNIC of the disaggregated memory node performs the data synchronization and releases the write logs in the background. Let's first focus on the fast commit protocol. Recent studies use visibility control and logging to merge the commit phase and commit all replicas in a single round trip. Specifically, they first make the data invisible at all nodes, then update the data, and finally makes them visible. This visibility control can guarantee data consistency. Unfortunately, this approach incurs additional overhead when using undue logs. Since undue log only contains stale data, the coordinators need to make the data invisible and update the data before the commit point. Otherwise, the new data will be lost. However, the batched RDMA atomic and write need a fence flag to maintain the ordering, which incurs an additional round trip. In contrast, the redo log contains the new data, and the order between the visibility and the redo logs does not affect correctness. So, it is possible to perform both operations in a single round trip. As a result, we adopt the redo log and the visibility control to merge the commit phases and commit the transaction quickly, as shown in the figure B. After merging the commit phase, let's review the original protocol. The validation phase checks whether the read site is updated by other clients during the execution and the locking phase, while the commit phase writes redo logs of the write site to all replicas. We find that there is no data dependency between the validation phase and the commit phase. So we further combine these two phases to reduce the network round trips. In this way, HDTX can shorten the lock duration and enable fast transaction commits. Some studies also propose combined execution and locking phases. Putting this idea together, this figure shows how HDTX processes a transaction using our fast commit protocol in DM system. It mainly includes 3 phases, but can commit a transaction within only 2 round trips. However, when there are high read-write conflicts, HDTX may roll back the commit phase due to unsuccessful validation. Fortunately, since redo logs can be overwritten directly, the rollback of the commit phase incurs rather low overhead. So, this design can significantly accelerate transaction processing, particularly for workloads with low read-write contentions. Now, discuss our further optimization for the commit phase. As shown in the top right figure, we use redo log for the commit phase, but it's costly to send the new data and log in 2 rounds of transfer in DM systems. Traditional monolithic servers rely on CPU to perform data synchronization to reduce the latency, because it only involves data copy locally. So, in DM environment, we plan to exploit the RNIC of the memory nodes to synchronously perform the data copy. We use the RDMA wait and enable primitives to allow the memory node's RNIC to copy the redo log, as shown in the figure. During initialization, we create 2 work queues in the RNIC for offloading. Specifically, RDMA wait, RDMA-enabled, and RDMA write are issued to work queue 2. Then, an RDMA receive is put to the Q1. The destination of the RDMA receive is the address of the RDMA write metadata. To start data copy, the computing node transfers the resource and the destination of the data copying via an RDMA send, referring to step 1. This RDMA send consumes the RDMA receive and overwrites the metadata. Meanwhile, it also activates the work Q2, referring to step 2. RDMA-enabled forces RNIC to fetch the new metadata of the RDMA write, referring to step 3. So, the RNIC can copy the data from the redo log to the data air via the RDMA write. In the same way, we offload data updates, version updates, and the lock release to the memory node RNIC via two RDMA write and a RDMA atomic primitives, without any interventions of the memory node CPU, and reduce RDMA bandwidth consumptions. Next is our third design. Most transaction systems face a risk of high tail latency due to local contention and deadlocks. Our goal is to manage and schedule local requests for transactions. So, we contrast two queues assigned different priorities for each lock in the memory node. We queue requests with the same priority in the first-in, first-out manner, using Laporte's bakery algorithm, and rely on coordinators to determine the order of the request by reading the lock object. Specifically, a pair of counter and max can represent a queue. Counter refers to the current request number, and the max refers to the total request number. For easy understanding, let's look at an example of lock acquisition. After initialization, all 4 segments of the lock object are 0. Then, a green coordinator requests the lock by issue RDMA fetch and add primitive to add 1 to NM. Since there is only one request, it obtains the permission and can modify the related data. A Liao blue coordinator requests a lock and modifies the NM to 2. Since there is no request in the priority queue, the blue request is the next one to acquire the lock. A Liao yellow request comes and modifies the NM to 3. It has to wait for previous 2 requests to be completed. At this point, an orange coordinator requests a lock with a high priority and adds a PM to 1. When the other coordinators read the lock object, they will find that a high priority request has arrived, and they will wait for the high priority request to complete first. So, the orange request instead of the blue request is the next one to acquire the lock. After the green coordinator commits a transaction and releases a lock by adding 1 to NC, the high priority orange one acquires a lock. The blue one becomes next in line. In this way, our priority-based locking can reduce the latency of mission-critical transactions by assigning them a high priority. Here is the experimental setting. We conduct our experiments in an RDMA-capable cluster with 5 servers. To set up the disaggregated memory system, we use 2 servers as memory nodes for two-way replication, and each node is restricted to use only one CPU core for cluster initialization. We disable the DDIO technology and configure the persistent memory in application direct mode on all memory nodes, allowing coordinators to perform remote durable write via RDMA read after write operation for durability. We compare HDTX with 2 RDMA-enabled transaction systems, Ford and Farm. The state-of-the-art Ford is designed particularly for DM system. Microsoft Farm is an in-memory distributed computing platform. that use RDMA-based remote process call to process transactions with memory node CPU. We adopt a derivation of FARM, in which the coordinators use one-side RDMA primitives to access remote data for the DME environments. We use three typical online transaction process workloads: TPCC, small bank, and TATP, as macro benchmarks to evaluate the performance of different transaction systems. We use 16 threads, with each thread launching 7 worker coroutines as coordinators. This setup enables all transaction systems to achieve near-optimal performance when using single computing node. This figure shows the end-to-end performance of each transaction system when using 3 macro workloads. Compared with Ford and FARM, HDTX significantly reduces the average latency, improves its throughput, and reduces its tail latency of TPCC and small bank. For TATP, HDTX and Ford show comparable performance because most transactions in TATP are read-only, and both systems allow all backup memory nodes to serve read requests for high throughput. Besides the macro benchmark, we also develop micro benchmarks to evaluate the effectiveness of our 3 individual technologies. Experimental results demonstrate that our 3 designs can achieve good performance gains. HDTX can reduce the latency by combining more transaction processing phases in the proposed faster commit protocol, and can also significantly reduce the latency by scheduling transactions according to their latency requirements. So, HDTX is particularly efficient for transactions with high read-write conflicts and write-write log contentions, such as TPCC and small bank workloads. Overall, distributed transactions usually are processed inefficiently in disaggregated memory systems due to high latency of remote memory access. This work presents HDTX, a high-performance transaction system that delivers fast transaction services and supports flexible transaction scheduling in DM architecture. HDTX merges multiple transaction phases with fast commit protocol by offloading the release phase to the RNIC and scheduling transactions with the priority-based locking. HDTX can achieve efficient transaction processing. And that brings us to the end. Thanks for your attention.